Hello everyone and welcome to Computational Methods. We're doing homework 1, which is titled Vectorization, Jacobian, Finite area, and 3D plotting. So shared on my screen right now is the assignment homework 1. Now this is going to be a 4 or 5 part series going over each of the different sections of this homework. So in general, we're going to be focused on a helical pipe, so a pipe that spirals. That's defined by these three parameters in x, y, and z direction. So in the first part 1 of this homework, we are going to code a function that will accept these functions and basically calculate the Jacobian of this curve. And then what we're going to do is Jax has an automatic differentiation. Basically, Jax can do a Jacobian automatically. So we're going to compare our function that we're going to make in this video with Jax's automatic differentiation function. So have here an empty sheet. So first thing we're going to do is import numpy because we'll need it for we'll need some of the functions out of it. Then we're also going to want to import Jax, and then we'll need Jax version of numpy. Okay. So let's run that. So first thing we're going to do is we're going to define our function, define the curve. Yeah. So we're going to use these three parameters and kind of build a function that will give, given like t values, it'll give us the xyz coordinates of this pipe as t goes from 0 to its final values. So how we're going to do that is we're going to define our curve, and then we're going to need the variables t, we're going to need variable r, and w, and then this guy here, the slope of z, which we'll call just mz. So r, w, mz. So those are going to be our 4 variables. So xyz for the xyz coordinates of this curve, and it's going to equal, so let's make an array using Jax numpy. Excuse me. Alright, so first the x. So x is 3 times cosine of t. So for our coding, it's going to be r times jmp dot cosine of t, of w times t. Whereas w is the constant that goes with the variable within the trigonometric function. Now, in this example, w is just 1, but I still think it's good to show in case you have to apply this to any others. So next, what we're going to do is we're going to define the y, 3 sine of t. So it's going to be r times sine of w times t. And then z is our slope coefficient, mz times t. So it's just mz times t. Alright, so now we got that. We're going to return our xyz. So let's run that, no errors. Alright, so there's our function. Now we have to actually give it values for these variables. So first off is going to be t, and we're going to do in space it's a numpy function. So we need mp in front. Let's get rid of this. MP boolean space, and we're going to go from start as 0, end, I don't know, we'll do 6 times numpy dot pi, and we'll do 54. I should give us a pretty nice curve as it goes along without too many sharp lines. All right, so that's T. Now our R from our example is 3, so we're going to set that equal to 3. W is equal to 1, and MZ equals 0.4. So these are our constants. All right. So let's just make sure it all worked. So let's do XYZ equals our curve. Then let's give its variables TR, W, MZ. All right. Sweet. No errors. That's a good sign. Let's see what XYZ equals. All right. So I mean, that array looks pretty convincing, but you really can't tell what it is by just looking at an array, at least not easily. At least I can't. So what we're going to do is we're going to make a plot just to see the curve. So let's make subplots. Row equals 1. Call. Normally I get a prompt here. That's what I normally use. Oh shoot. Yeah. It's from plotly dot subplots import make subplots. So we have to make sure we import it first because it's an external function. So now it should be happier and it should hopefully function. Yeah. This is the way you do it. Ah, here we are. So row is equal to 1, call is equal to 1. And we want to specify it as a surface plot, which means we have to give it a dictionary, which I believe is parentheses, parentheses. Then we're going to give it the type surface. Okay. Then we're going to the figure that we just made, we're going to add a 3D scatter. There's supposed to be an underscore here. Okay, I think that worked. So let's do XYZ. So now we're calling the actual array that we made earlier. And if you remember from this, so we had all the x values in this first row, the y's in the second row, and the z's in the third row. So what we're going to do is for the x, we're going to call all values in the first row. So row 0, every column. Then for y, we're going to do the same, just we're going to call row 1. and then z equals xyz row 2. And two of those. Invalid syntax. Oh, there's your period. So this is what our curve looks like. Let's get rid of all of these. Let's get rid of the dots. So we'll do mode equals lines, and we'll do update layout. We'll make it, yeah. I'm going to make it be dark, so it's a little bit easier to see. Underscore dark. There we go. So this is our curve. It's a nice helical curve in 3 dimensions. Move it around. Okay, so this is the curve that we just generated, and that's nice and all, but the real purpose of this first part of the homework is to basically generate a function that can calculate the Jacobian of this curve here. So let's go ahead and do that. All right, so in this step, we're going to actually create a function that can calculate the Jacobian. So let's call it Jacobian underscore test. All right. So what it's supposed to do is it's supposed to take a function. So to denote the function that we're going to input into this function, we're just going to call it f. So within this one, we're going to define another function and just call it Jack for Jacobian. And this one, we're going to give it an x and a dx. All right. So a bit of background about what a Jacobian is. So Jacobian is a matrix of the partial derivatives of a function. So in our case, we have one function, but we have 3 separate parameters, 3 separate functions that go into this one curve. So for us, when we do these partial differentiation, we'll do it in respect to t. So our end result is going to be a 3x1 matrix that is partial derivative of this with respect to t, partial derivative of this with respect to t, partial derivative of this with respect to t. So the way we're going to go about calculating this Jacobian is we're going to use basically the functions of derivatives. So derivative. So a derivative, as you know from calculus, is just the slope of a function, the rate of change. So a way to kind of approximate it is with this limit here, so which basically says that you can kind of estimate the change of something by taking the function at some value a, adding a tiny bit, and subtracting the original value of that function at a. Then dividing that all by that tiny bit that you did, and that limit, as your h approach is very small, will kind of give you the slope of that function at a. So when we're going to code this, we're going to code it that way. So our x is going to be our a in this example. So it's going to be the point that the function is being calculated at. And our dx, which will actually we'll just give that a value, 1e negative 8, very small number. That will give us a decent approximation of a derivative by hand. So what we're going to do is we're going to take our function that we're pulling in from here, f of 0, and define it at x. Okay, so that'll be that value there will be this f of a here. Okay. So now that we have this, we're going to do we're basically going to iterate it for all the x values that we're going to be given, because we're going to give x as we could give x as an array. So let's do x dot size. In range. Okay, looks like it has to be in parentheses. Okay. So now we're going to do x total, and we're going to set that equal to x total. No. X tot is going to be this guy right here. So what we're going to do is we're going to initially set it as just a. So our x tot in this for loop is just going to be x sub I, or the index I in that array that we're going to be giving, plus our dx. So that's going to be our tiny little iteration, tiny little increment that we're going to be doing with this. All right. So that's our x tot, and then we got our j, which is our actual Jacobian matrix, is going to be, we need to make it a matrix, so let's set that equal to, and now what we're going to do is we're going to put in this guy right here. So that's going to be our a plus h, this guy. Make sure we get the parentheses right. Yeah. Minus f sub 0, which we defined up here, divided by dx, which is, again, this little guy right here. And then finally, we're going to return j. We want that. And then for this guy, we're going to return our jack. It would help if I could be able to spell. All right. So it's cool with that. J is not defined. Okay, so that means we probably should define j up here. So j equals np 0. Then we need, so let's just make j just an empty, a matrix full of zeros, and then we'll populate it later. So we need to give it its shape. So so the rows it needs are going to be the size of FO, and the columns it needs are going to be the size of X. Does that work? find it. This. Let's give it a try. So the way we're going to do this is the function we're going to give is going to be, let's just close these outputs so we can scroll a little bit easier. So the inputs we're going to give this test is going to be this curve here. So we're going to call Jacob equals Jacobian test. And what we're going to do here is we're going to use the lambda function, which will just be able to, when we give it this curve, it'll specify that t is the variable that's changing. So lambda t curve t r w and z. Yeah, it worked. So now let's give Jacob value of 0. That'll be the starting x value here. And float has no. Okay, so I think it doesn't like the fact that our f0 is a float instead of an array. So what we're going to do is we're going to tell it that it has to be I don't remember the function, but essentially there's a function that you can say that it needs to be that if you give a variable, if it's not an array, it turns it into an array. So let's see if I can, so it's numpy float to array. No, it's something like at least 1D maybe. That's this. Convert inputs arrays with at least one dimension. Okay, so that's the one we want. So that's numpy at least underscore 1D. Going back here. At least underscore 1D. F sub 0. And I'm assuming we'll have to do the same with x. So let's just get that out of the way. P dot at least 1D x. Alright. So run that, run that, run that. How about more errors? Cannot interpret 1 as a date type. That was new. So, okay, so it's with this line. So let's see what this one's. Shape. Shape like. So does it want double parentheses? So we got parentheses. Let's try it. So f0 dot size comma Jax dot size. Worked. So we got 0.3.4. Pretty much 0.4. Well, so there's our function. And now what we're going to do is we're going to compare it to the Jax auto differentiation. So now what we're going to do is we're going to compare this value we got here with Jax's auto differentiation method. So I believe it's just Jax dot Jacobian. Then we have to give function, yeah. So then, oops, that. Then we're just going to copy and paste this. Then let's name that Jacob Jax. What's that? And we're going to make that Jacob Jax 0. Voila. So as you can see here, we have two arrays, 0, 3, and 0.4, 0, 3.4, and this function that we made, following the rules of derivation, derivatives, is equal to Jax's auto differentiation. So let's try it at 0.1, or try it at 1. So run that. Doesn't seem right. That doesn't seem right. I would expect, knowing what I know about derivatives, I would expect at least that third z value to be 0.4 or thereabouts. Let's see what. So yeah, so Jax's Jacobian gives us this value, whereas ours gives us an array of zeros. So that means we're not quite done yet, unfortunately. We got to figure out what's wrong. All right, so let's set this aside for now. Can we access what J is? No. Okay. So what I want to see is I want to see what this J is. Now that I'm looking at this, I'm seeing that we are giving J, we're feeding it these values and telling it to go into here. But really, I think we should put the same kind of array notation here. Maybe that'll. That was not the answer. So too many indices for array. Total. That should solve our problem. Didn't know I needed to define it. I thought I could just. Do I have to say x equals x? Is I happy with that? Just curious. So it worked. It did calculate, but it's not the same value at 1. Curious if it's the same value at 0. Nope, not 0 either. So if x might be changing. Let's try making this a copy. Remember our professor mentioning something about a copy. Nope, that didn't make it. That didn't change anything. At least I was happy about us defining the x total in the first place, though. So, after looking through my notes and kind of testing the code on my own, I found the problem. So, the problem was that I was defining x as an array with one dimension at least. I was doing it too late. So, because this uses x as a way to calculate f0, I need to have defined it beforehand. So I am going to do that now. Move it there. Test that, turn, voila. So just a reminder, 03.4. Now let's test it at 1, since last time we tried it at 1, and it didn't like that. So let's test this one at 1, and ta-da, they're equivalent. Perfect. So just make sure we've done everything we're supposed to. So we explained and coded a higher order function that accepts our curve and the functions that go along with it, and calculates the Jacobian of that central helix. And then we compared our results at specific points with the Jack's Jacobian automatic differentiation. So join me in the next video for part 2. Hope to see you there.